Okay. Um, uh, Sure two. Today is like 1/22. Okay. So what I was going to tell you about today, it's something called clustering, which is a useful idea, but that's like as a motivation to discuss like equivalent relations, which is an important concept and it gets used from time to time, but it's like I'll illustrate it with some examples that hopefully like feel interesting. Um, so I'll just tell you first what a relation is, and then you can talk about what an equivalent relation is. So a relation, you can just think about it as a real generalization of a function. So it's like a generalization of a function. Okay. Um, so like just take the most basic function like f of x equals x squared, like, for example. So if you write something like that, there are many ways to like think about the function. One which is like the most common way to study the function, like usually like in a pre-calculus course, or calculus, it's like, in terms of like the graph, right? So you would draw the graph of the function. And you think of the x-axis as the domain, the y-axis as sometimes it's called the codomain. And the idea, like, when you start up giving it different values, right? Like if this is 1, that corresponds to 1, right? Or if you have like 3 here, that corresponds to 9. Um, and then if you had, let's say, -3 here, that also corresponds to 9. So, like, one way to draw this out is that, like, of course, it gives you a point on the graph, but you could draw kind of like more like a kind of like an arrow, like as I'll do here. Like if x is 1, you get this point on the graph. But so from this, like the way I'm thinking about it now, it's kind of like, oh, you're using the function x to kind of like connect the number 1 with the number, like the number 1 on the x-axis, right, with the number 1 on the y-axis, and same with the others, right? So if you have like the number 3 here, right, in the input, right, like the output is 9. So kind of like the function is establishing some sort of a connection between the two, or like a relation, we'll talk about in a moment, right? Um, so And then in the case of the function, right, as you know, the idea is that what makes it a function is that any number on the x-axis can only be connected with a number on the y-axis, but a number on the y-axis can be connected with multiple numbers on the x-axis, right? So -3 is also connected to 9 here, right? So you can say that like just to kind of to use a notation which is similar more closely to what I want to use with the relation, you can say that a number x, right? So if you have like a number x, and this is like the usual notation for a relation. Well, it's going to be related. Well, actually, let me use like I'll write it R for related. Okay, so this like the way to say this is like x is related to y. So you're going to say that x is related to y in the case of this function. whenever y happens to be at square. Okay, whenever y equals x squared. So like, for example, like what I was showing you now is like, say, three from this perspective, like the number three is related to nine, right? Because nine is three squared, right? So like here, like three is related to nine, since nine is three squared, right? Or negative three is also related to nine, since nine is negative three squared. But like, just let's say the example, like three is not related to zero, right? Because zero is not like that's three squared, right? So three is not related to zero. Usually when you want to say that something is not related, you kind of like cross it out to say that, oh, this is not related. This is not related to zero, since zero is not three squared. That kind of makes sense. Now, what happens is in the case of a function, the idea is that in the case of a function, like x can be related at most with one value for y of y, because that's the idea that one point in the input can only have like one output. So for a function, like for a function, what happens is that x is related x or y for at most one value of y, since the definition of a function requires like, the input to only have one output. So just to kind of like show you the idea is that you can have relations that for which does not happen, this does not happen. So here's like another one that you actually will recognize, but here's another example. Let's see. Here's another example of a relation. Example two. I promise you'll see why this is all connected to the stuff I was saying last time. But you could say that two numbers, x and y, are related. X is related to y if x squared plus y squared equals 1. Okay, if x squared plus, or just to make something actually easier for my numbers, x squared plus y squared equals 2. Right? Which we kind of know is a circle, right? Like x squared plus y squared equals 2, right? It's a circle, and that actually is connected to, what you were told that the circle is not the graph of a function, right? So you could have, here's some things that happen. You could say that, for example, 1 is related to 1, right? Since y, let me write it, that, oops, 1 is related to 1, since 1 squared plus 1 squared equals 2, right? But also, like, 1 is related to negative 1, right? Since 1 squared plus negative 1 squared also gives you 2, right? So, again, in this case, I can think I can try to fit this all in the picture. In this case, like this relate, I mean, I'm choosing examples where we kind of like already know the answer for what's going on, right? Like the idea is like, exactly one value of x would if there's like any relation at all, will be related with like two values for y, right? In this case. So if you had like a value for x here, there would be two y values that it relates to, right? Um, except the at the equator, right? Because at the equator, there's only one y value where that happens. So I'll write that down. So uh, there's like a y value here, and there would be another y value here, like negative y if you want. But if you happen to be on the equator, right? There's only one y value to which you are related. So let's say like this. Um, if x is related with y, then x is also related to with negative y. That's one way to think about it because it's symmetric, right? So that gives you, so x is related with um, two y values if it is between negative 1 and 1, if x is between negative 1 and 1, right? If x is 1 or x is negative 1, that's actually only related to one y value. And if x is larger than 1 or smaller than negative 1, it's related with no y values, right? Because uh, so if x is 1 or negative 1 or 1, then x is related to just one y value, to only one y value. And if x is greater than 1 or x is less than negative 1, right? Meaning that you're outside, the radius 1, like circle, then x is not related with any y, right? Oh my God, yeah, it's because it's a square root of 2. Oh my God, that's like yeah, like a square root of 2. Yeah, I think I'm glad you caught that. I had to be penalized at some point for choosing like, yeah. Oh my God, like that's why you should always choose the unit circle. So now this looks horrible, but I'm glad you caught it. Uh, okay, 20 y values. Again, like these two examples, hopefully it's just kind of like as a warming up, but the idea is that, okay, this is like an example of a relation where like that doesn't correspond to a function at all, right? Let's see. A single x value is kind of like being paired could be paired with 0 y values or with one y values, but those are kind of like the extreme situations. But they're all paired with like with 3 by speed. So okay, so far so good. Okay, now we start with a slightly more interesting example. So now, I want to switch notations because usually if you write x and y, you're thinking that, you know, the x and y can take any real number values. When you're thinking about integers like, 1, 2, 3, or -4, -5, -6, 0, they usually do give them like letters m and n. When you're thinking about integers, that's like a more common notation, kind of like number theory or discrete math. So here's another example. So now m here now m and are integers, positive or negative, like they could be either positive, negative, or zero. Like, if you always want them to be positive, usually sometimes they're just called like natural numbers, negative or zero. Okay, so here now the relation is that you're going to say that two numbers are related if their difference is can be divided by two. Okay, so now the idea is that now the relation is that m, the new relation is that m is related with n, provided that m minus n is divisible by 2. Maybe some of you have seen this example, but it's a useful example for what I want to do in a moment when I do something slightly more interesting. So, like, just like to start with some special cases before I say something else, like, so for example, 2 is related to 4, right? Because what? 2 minus 4, that's just like -2, which can, that is a multiple of 2. That's just 2 times -1, right? But like say 2 is not related, like I cannot put like cross it out with, you know, 2 is not related with 3, like, in the sense of division, like, because 2 minus 3 would be -1, and you cannot divide that by 2. Well, if you can, but you get -0.5, which is not an integer, right? Like, so, like, in that sense, you're not allowed to divide by 2. But it's not a multiple of 2, that's what I mean. Uh, and maybe as you can imagine, like, in this case, what happens is that any two even numbers are related with one another, and any two odd numbers are related with one another, right? So, like, the idea is that if you have an even number that is related with another even number, and like almost by definition, right? Because an even number is a multiple of 2, right? Like an integer does multiple of 2, and then an odd number is related to an odd number, right? But an even is not related to an odd, nor an odd is related to an even, right? But even is not related to odd, and odd is not related to even. Oh my God, what just happened here? Still getting used to. Okay, so far so good. Now, okay. Let me do now two kind of like more like sociology example. So you could say two students are related. I mean, I guess there's only you can only major in one thing, right? And you have minors, but okay. So two students are related if they are majoring on the same thing, right? So here's like a relation between students. So student one is related to so S1 and S2 just means student one and student two, right? So student one and student two are related if their majors are the same. Okay. And I'll compare it. Okay, let's see. I'll okay, instead of using the letter R, I'll use the letter M for majors. So, like, I'll say S1, M, S2, like majors, right? So they are related, but I'm just calling it R for like to just kind of give it some more like a meaning. So just think of M here as R. So two students are related, they have the same major. And now let me give another example of a relation, which like, I'll call it F for friendship. So two students are F related or like F for friendship if they are friends with one another. Okay. Okay. And here's another one. So S1, F, S2, if the students are friends. This example will actually be useful for like a clustering thing that I'll tell you in a moment. So I'm bringing it up for like strategic purpose. Okay, so like what I want to kind of like compare is like how like what certain properties of are kind of like in common of these two relations and what which others are not. So oh, and then uh let's just do another one just kind of like to distinguish them. Okay, and I'll do S1, T, S2, T for tutor. So S1 is related to S2 if the first student ever tutored the second student, like for a class. Okay, so okay, so we have three types of relations. One is like two students are related, they have the same major. Two students are related if they are friends, or two students are related if one student tutored the other. Okay. Okay, so just to kind of follow a lip service to like one community terminology, Alice and Bob will be my students. So like there's a difference between, I mean, there's some differences that you can already tell between them because if I say Alex and Bob are both majoring in biology, it doesn't really matter which one I name first, right? If you say Alex is majoring in biology and Bob is majoring in biology, like this is the same that Bob majoring in biology and Alex majoring in biology. Uh, you know. But like for example, with tutoring, right, it does make a difference if you said, oh, Alice tutored Bob. It that's not the same as saying that Bob tutored Alice, right? Like that definitely does have like distinct meanings, right? So you could have like a situation, like for example, so it is totally plausible, right? You could have like a situation where you could have that Alice tutor Bob, right? That's what I mean by here, like Alice tutor Bob, right? Alice tutor Bob, but it's not true that Bob to Alice, right? Like that Bob tutor Alice. It may not be true. Oh my God, I wrote it as B. Bob T Alice, right? Does that make sense? So you would say that the third relation is not necessarily symmetric. Okay, so the third, like now I'm starting to throw in some terminology. So the third relation may not be symmetric, right? So depending on the populations you're talking about, right? So so relation T, and now I'm about to give you you know a definition in a moment. So relation T may fail to be symmetric. Oops, what happened here? Symmetric. Oh, actually, I'll put it in colors because like it's a kind of like a definition. And so what does it mean for the relation to be symmetric? It means that if X is related to Y, then Y should also be related to X. So it's kind of like, like it doesn't matter in which order, like you write like the entries of the relation. So what is the definition of a relation? And I'll use the letter R just to go back to like kind of like the more standard definition. So let's think about it as a definition. So you would say that a relation R is symmetric if X is related to Y whenever, like, if and only if, like, like, how should I say? If whenever, like, I don't want to use too much like mathematical logic notation. So that's why I'm trying to avoid like implications and all these weird like symbols. If whenever X is related to Y, we have that Y is related to X. Another like another relation that's not symmetric in biology is like lineage, right? Like so you could say like two organisms are related if one is a parent of the other or like an ancestor, right? Like an ancestor of the other. So ancestry is not symmetric, right? Because um if you're my dad, I'm not your dad. So like that is like there's kind of like a directionality to it. But in a symmetric relation, in a sense, there's no directionality, because both sides kind of like work. Now, friendship you would expect in the ideal world that is symmetric, as in like if I'm your friend, then you are my friend, and I'm not just like like delusional that like like we're friends. So like just for like sake of it, let's just pretend that friendship is like that like F is a symmetric relation. So no, one would hope F is symmetric. So let's say that example F is symmetric. Again, like being charitable, and the majoring one for sure should be symmetric, right? Because if you major in biology and I majored in biology, like again, like that is a symmetric thing. Both we both have the same major, you know. That you can just say that like either way. And so it's so far so good. So like whenever you have a relation, it's very useful to know whether it's symmetric or not. Okay. Um, so like if you wanted to think about it kind of like as a graph, you could like think about like a network or something where like you have like the people, right? Like Bob, Alice, then Charles, right? Then Diana, I don't know. And so like, if you were trying to represent like friendship, right? And the friendship relationship, then like assuming again the friendship is symmetric, you can kind of like draw, you can just draw like an edge between the two of them whenever they're friends, right? So if they're related, you draw an edge. So you can think of this as nodes of a graph, right? Like so you have a classroom just with 4 students, you want to determine who's friends with whom, right? So there are 4 vertices for the nodes. And then if we said that Bob and Alice are friends, maybe Bob's popular, so he's friends with everyone, right? And maybe Alice and Diana are friends, and then Charles is only friends with Bob. But because it's symmetric, you don't have to specify an orientation, right? Like Because if you wanted to, if you only went one way, then you have maybe you would like to do like an arrow to indicate who is friend, like that I'm your friend, but you're not mine, or something like that. So that like like what, and now you're seeing maybe why that's kind of like a useful idea, like for like these data stuff, because like it gives you like a nice representation of like the set that you're working with. So again, like just to kind of like just to write it here. So you have Alice, and then you have Bob, Charles, Diana, right? So you again, like we said that Alice and Bob were friends, Bob and Charles were friends, Bob and Diana were friends, and then I said I think that Alice and Diana were friends, right? So it doesn't matter, this is actually what people call like an abstract graph, you know, because like for example here it looks like they are crossing one another, but that's kind of like just like an illusion of the fact that we're trying to represent that as a picture, right? Like you just have four people and like a list of relations between them. So once you have to draw it out, yeah, it may look like, if you think of them as bridges, oh, they're colliding, but that's kind of an illusion, right? Because people even lift it, like, if you lift it up this a little bit, then they're no longer like, intersecting. So like the intersection means nothing in this context as of now, because it's just like what people call like an abstract graph. What I'm trying to say is that here, so you can represent each of the like students, like, as a node also, or like a vertex. So each student represented as a vertex or node, and you draw edge an edge whenever they are friends, right? The fact that this is symmetric means that it is not ambiguous. Like you don't have to put like an orientation to the graph. Like you don't have to or kind of like put like an arrow. Since this relation is symmetric, you don't need you don't need uh, an orientation like arrows like on the edges. Yeah. In a case where like the relation is not symmetric, like a genealogy tree, kind of like the standard thing is more like to stack them vertically, right? Like so, you put your parents above you, your grandparents above you. So like kind of like that's kind of like giving you like the orientation, right? Like the fact that some are above the others, right? Kind of like in a hierarchical way. And when the relation is symmetric, like that does not happen. Okay, that makes sense. Um, and then okay, so understanding if a relation is symmetric or not is very important. Another useful property is transitivity, so which I'm going to define now. So, you know, transitivity just means that, if, like for example, I'll write it down first and then I'll kind of like illustrate it with these like relations. So it's transitive whenever X related with Y and Y related with Z guarantees that X is related with Z. Okay, so for example, the majoring, like having the same major, that's a transitive relation because, so here's an example. The relation M from before is transitive because what? Like, if you knew that Alice and Bob have the same major and Bob and Charles have the same major, then for sure Alice and Charles have the same major. Like that kind of like forces it out. So because if as one student, well, let's just use Alice, Bob, and Charles, right? If Alice is related to Bob in the sense that they have both the same major, and Bob is related uh, to Charles in the sense that they both have the same major, then that forces Alice and Charles to have the same major. Age, age is another relation of that sort, which is transitive, right? Because if, we are both 20 years, Alice and Bob are both 20 years old, and Bob and Charles are 20 years old, about that, it kind of like seems very soft, but like then Alice and Charles are both 20 years old, right? So that kind of like, it kind of like, propagates in a sense. Friendship is not necessarily transitive, right? So if Alice and Bob are friends, and Bob and Charles are friends, that doesn't mean that Alice and Charles are friends, right? So like the relation F, the friendship relation is not a transitive one, right? On the other hand, um, the relation, and also like the tutoring one wouldn't be transitive either, right? Because if Alice tutored Bob and Bob tutored Charles, it doesn't mean that Alice necessarily tutored Charles, right? Uh, Oh, here's like, okay, just to go back to math, like here's like a relation in terms of vectors, right? So you could say two vectors are related if they're orthogonal, right? So they're like in 90 degrees, right? So you could say, here's another example, just to go back to math for a moment. So I won't draw the arrows, just like here, let's say U is related, vectors UV are related. So U is related with V, provided um, U and V are orthogonal. All right, so again, like that's orthogonal perpendicular, right? I always do that like a true false in calc theory. So like definitely that's going to be symmetric, right? Because if U is orthogonal to V, then V is orthogonal to U. That's fine, right? So notice that this relation is symmetric, right? But now, what do you think? Is it transitive? If vector U is perpendicular to vector V and vector V is perpendicular to vector W, is it the case that you're saying no, right? Like, what is a counterexample? Right, like you could do the negative, right? But not transitive, right? Because, for example, you know, the vector I, like the vector I from ijk, I is related to J, right? And say J is also related to negative I. Sorry, negative I meant. And it may feel like a bit of a cheat, but So, so I and J are perpendicular, J and negative I are also perpendicular, right? But I and negative I are definitely not perpendicular, right? But But one that is symmetric and transitive with vectors would be to say, like, for example, two non-zero vectors are related if they're parallel. So that one does work fine, right? On because what does it mean for two vectors to be parallel? There one is a scalar multiple of the other. And if you just go through like what it means, like for that to happen, if U is parallel to B, so B is kind of like an elongated or contracted version of U, and W and V is related to W, so W is kind of like a stretched out version of V maybe, then W is going to be like, again, like elongated or contracted version of U, because like they're all kind of like all pointing in the same direction, or opposite direction, but that's also fine with parallels. So one that's transit asymmetric, sorry, transitive asymmetric, I need reflexive, which is like the one that's missing like property, but like a different one, saying two non-zero vectors UV are related, URV, provided um, they are parallel. This one is symmetric and transitive. No, okay, almost done, that's almost done with the definitions. But again, it's useful to understand these properties about a relation. So a relation could be symmetric or not, could be transitive or not. The other useful thing of property that is usually defined for a relation is being reflexive. So a relation is reflexive if any of the objects is always related to itself. So it's kind of when you see yourself in a reflection, right? Like that's like in the mirror, like it's you with yourself. So that's the last important definition for a relation. So the last that's which is usually sometimes like the first one that gets defined because it's kind of like the easiest to state, but like the others are more like interesting questions. So reflexivity. So you say that a relation is reflexive if it's always a case that X is related to X. So if regardless of X, we 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 have that X is related to X of what X is. Again, I'm trying to write it down. We are quantified for that. Put a bit more natural. So for example, let's just go down the list of the ones that we have talked about. So the majoring relation is reflexive because you have the same major as yourself. Okay, right? If you're a biology major, then you are a biology major. It's almost like circular, right? Like so being for like the majors thing, you know, um the major relation is reflexive, right? Because no matter which student you pick up, a student always has the same major as themselves, right? Since any student as themselves, like, like it kind of like, even sounds weird to just say it out loud, as majors as, Alex has the same major as Alex. That's all that this is saying, right? Uh, the tutoring definitely is not necessarily reflexive, right? It's kind of like weird to say that I mean, you could say, I guess, if you say that you self-tutor yourself, you're just saying that you studied, right? Like, if you don't call it tutoring, right? Like usually that requires two people involved because then you're just studying. So like you wouldn't say that tutoring is reflexive, right? So like that would be an odd word, use of the word. Like tutoring relation is not reflexive, right? Since like yeah, like you don't tutor yourself in sense, or and that's not like a common use of the word, right? Since a student is not its own tutor, it doesn't tutor. It's not its That's just called studying, right? The orthogonality, right? Like the two vectors being orthogonal, that's also not reflexive, right? Because a vector is not orthogonal to itself, right? Like a vector is not perpendicular to itself, unless you're the zero vector, but that's kind of like the extreme case, right? That only happens once. So with the vectors being orthogonal, that's also not reflexive. Since only the zero vector is orthogonal to itself. But the one about being parallel, that is fine reflexive, right? Because a vector is parallel to itself. It's just like the scalar, the rescaling is just one, like the number one, right? Vectors being parallel is an orthogonal relation. Sorry, not an orthogonal, I meant reflexive relation. I think the parts of it. Okay, and why am I throwing all this terminology? Because, kind of like the best relation in a sense that you can be is one that's reflexive, symmetric, and transitive, and those are called equivalence relations. So like kind of like in the hierarchy of relations, kind of like in the matrices, right? What is that one of, we have to be a matrix, what would you ask for to be like a symmetric matrix probably? Like, I mean, there may be a few other choices, but there are not many to choose from. Almost like a symmetric matrix is kind of like the best you can be. So if you're a relation, the best, almost like in a sense that you can be, is like as an equivalence relation. That's the name for that. So an equivalence relation is just a relation that's, um, let me write it down. So maybe next page. So I'll show you why that's useful because it creates a partition. So I'll tell you what that means in a moment. So this is a relation that is, uh, so both like the three conditions need to be satisfied: reflexive, symmetric, and transitive. So, and again, the reason why they are nice is because they kind of like chop up, they break up the set that you were working with into subsets or regions which are disjoint. So that's called like the partition. Now, so let me just start with the case of the major relation. So we were saying that the students are related if they have the same major, right? So that is definitely going to be an equivalence relation, right? Like it was reflexive, you have the same major yourself. We talked about biosymmetric and transitive, right? So here's an like an example was like the majoring relation is an equivalence relation. So what that means, like again, like if you kind of want to do it diagrammatically, you could have kind of like you could have like a graph, right? Like each node in that graph is like a Rutgers student, right? So you have like, oh, somehow I think of biology as being green. So like, you have like you have like, like student one, if they are related to student two, it's because they are both biology majors. If then related to, well, student 100, they're listed some way. So, these would be the biology majors, right? I'll just do two more majors. Like, right, so like maybe like so the biology majors are all related to one another. So like I should also draw an edge between one oh, let's just say that they're like like let's say 10 students. Like it's just like to draw everything more accurately. So again, because every time there's like a relation. So S1 is related to S2, S1 is related to S10, S2 is related to S10, and yes, like that's fine. It's like what, yeah, bringing all of them together. So like in this graph, all these like three students are related to one another because they have the same major, which is biology. And then like, you could have just like two people are majoring in math, let's say, so only S3 and S4 students, 3 and 4 are math majors. And then, okay, we'll have with the physicists like 5 majors, 5, 6, 7, 8, 9, 10. Sorry, S5. Oh, the fact, actually, I should add this, like the fact that it's reflexive, that means that you're related to yourself. So you can do like a self loop, also like just to represent that actually more accurately. So, which actually make me wanna put just like 9 students do not draw like a gigantic like graph. Let's see. So, and again, S3 is related to itself. Yeah, I almost forgot about that. So, okay. So then 5, 6, 7, 8. Good. So each of them so these are the physics. Oops. Mhm. What's happening here? Ah, what happened? Sorry, let me just go back. For some reason. Ah, fine. So the physics majors. Well, in fact, it's kind of like a combinatorics problem, right? Like how many edges you have to draw, like if you have like a subset of the student body. I'm terrible at combinatorics. I'm not going to try to give you the answer right now, but it's like it's probably one of these n choose a k kind of thing. So each is related to itself, and then you draw all possible like edges between them, right? So and sometimes it's called like well, if you just look at one, it's called complete graph because all of the vertices are connected to all the others. Like and one of these in isolation, right? Like because it's not complete because there's no edge between these three, right? But within each major, you're drawing all possible edges from this sometimes called like a complete graph. So 5 is related to 6, 5 is related to 8, 5 is related to 7, right? Then 6 is related to 5, which I already counted because it's symmetric, right? So I don't have to worry about like the arrows and all this stuff. 6 is related to 7, 6 is related to 8. And the only thing that I'm missing, I guess, right, is 7 and 8, right? Like that's it, right? I think, and that covers everything. You see, the reason why it's called like a partition is because it's kind of like breaking up the student body into regions, right? And none of the regions speak to one another, right? Like so, in terms of majors, like if your major is biology, it's definitely not like math nor physics. So the idea is that kind of like you chop out the space into independent, like, non-interacting regions, if you want, or the graph, if you want to think about it that way. Um, so there's no overlap, right? So like it breaks up like the set that you started with. In this case, my set was like the 9 students, right? Like the kind of like I subdivided it into three components, three blocks without overlap. So that's what the equivalent relation does in general. So that is essentially what the equivalence relation does in general. So let me write that down. Another easy equivalence relation to understand among social science, right? It's just like age, right? Like so, if you have the same age, that's an equivalence relation. And what are you breaking up the population by age, right? Like so, just like people with age 10, we put people like like just counting deep, right? Age 11, age 12, they are like all in different blocks, right? So in a sense, being an equivalent relation is kind of like breaking it up in terms of like a certain property, right? And all the people or like all the elements in one of the blocks have this same property, which is not being shared among in any of the others blocks. So an equivalence relation, the set, into disjoint, I mean, blocks or, which are called partitions. In the sense that there's no overlap, in that sense, there is no overlap. Does that make sense? Okay, so now to do something a little bit more interesting, still in the couple minutes I have left. Okay, then once you understand that you can build like equivalence relations, in a case where that's useful, well, I'll use it for linear algebra next time with vector subspaces. So I'll create like a relation on vector subspaces, which is called a quotient space of a vector space. That's kind of like a useful idea. But we kind of just to stick with these more concrete examples. Let me do something which is related to something called clustering, which we will talk about later on, but I'm just gonna give you like a brief introduction to what clustering is. So I'll do kind of like a very dumb example first, and then I'll do kind of like a more advanced one, like on the show you like an animation of how that works. Um, Okay, so let's say, uh, okay, so again, just to make it concrete, let's say that I have 9 points all placed along the number line. So I'll draw the number line. Okay. I'll draw the number line and I'll have 9 points. And these are like the coordinates of the points. So I'll put 1, 2, 3. Okay. And then like I'll have, again, it's like a silly one, but then I'll show you something a bit more interesting. 5, 6, 7. And then I'll put one like 3 apart. -2, -3, -4. Of course, you can more complicated it up, and you just imagine that you made like those sort of 9 data points, right? Like, it may not be that they are like placed on the number line. It could be in 2 dimensions, with 3 dimensions, or for them like 5 dimensions, like But it's in general, it would be like a finite collection of data points. But I'm thinking of each of these as a data point. Um, Yeah, like a 2 dimensional example, it's kind of like maybe a map of the Earth, like a 2D map of the Earth, and you just like the XY coordinates of like some major cities, right? Like, Paris, like, like London, and, like, well, New York or whatever, like, so you have like the data point, like just like certain specific cities, and then the XY coordinates of those cities in the map, like, okay, so let me write this relation first, and then we'll fix it, and you'll see why this has to be fixed. But you can say that x1 is related to x2 if the distance between them, right? I'm doing it like in 1 dimension, so like the distance between 2 points is just a given in terms of the absolute value, just to be very concrete, right? So the distance between them will be the absolute value of x1 minus x2. So let's say that that is less or equal to some threshold, so some number which I'll call epsilon. So actually I'll put like an epsilon, let's see. Well, I don't want to think about it as necessarily a small number, which is maybe what I would put. Like I may suggest if I'll put it like R, like. Well, if the distance between the 2 points is at most R, and I'm going to do it in a concrete case. So their distance is at most R. Okay. So for example, if R had been 1, right, my relation is that 2 points are related if the furthest away from one another is by 1. Like, okay, so if R is 1, so if R equals 1, so x1 is related to x2 if x1 minus x2 is less or equal to 1. And we can start with 1 just for, because we can start with 1 just like to kind of see what's going on here. So What do you think? Okay, is this going to be reflexive? What is? Right, like I mean, a point is actually at a distance zero of itself, right? So that's definitely less than one, right? So a point is okay, so definitely it's reflexive. And how about symmetric? It's also symmetric, right? Because like the distance between 2 points is actually asymmetric. In fact, I give you the definition of a distance function in general on a topological space, you always require that the distance of x to y is the same as the distance of y to x. So reflexivity and symmetry are for free almost of what it means to be a distance, like how you measure distance. So this is, and of course, like the one doesn't make doesn't play any role here. That's generally true regardless of the value for R. So regardless for any value of R, this relation is always of R. This relation, I'm almost okay, is reflexive and symmetric. Okay. But what do you say about transitivity? It doesn't look transitive, right? Because like for example, that's why I chose like very simple numbers so that you could see it, right? Like not like even here, like it's not transitive, right? Because -4 is related to -3 because they're separated by distance one, and -3 is related to -2 because they're separated by distance one. But it doesn't follow that -4 is related to -2, right? Like, they're actually a distance two, right? So, but in general, this won't be transitive. Okay. So there is a way to kind of like fix that, for lack of a better word, we force it out to be transitive, which is kind of like, this is called like single linkage clustering, where you say that they are related if they can be connected by a sequence of point of distance as most are. So you kind of like allow kind of like a chain of connecting points all within distance r, like between two pairs, so between any 2 points. So but, and I'll continue this next time because I almost done, I ran out of time. But there's a way to fix this, a way to fix this relation. I mean, I'll put fix in quotes because there's nothing wrong with it, but to fix this relation and make it transitive. And this is called like single linkage clustering. It's called single. Oh my God, what is this called autocorrect doing? Linkage clustering. And so the idea is to say now that 2 points are related if they can be connected by finally many points, all two pairs, the pairs like being all like within distance less or equal to R. So you can say, I mean, it's a little bit of a tedious way to write it in the notation, but you'll see in the picture that is really easy to understand. So you say now that like now X, use it like this. X is related to X prime. Again, X prime has nothing to do with derivatives, just to kind of like to not, I don't want to call them X1 and X2. If you can find endpoints X1, X2, X3 up to Xn, such that you'll see, okay. So the idea is that the distance between X and X1 is less or equal to R. The distance between X1 and X2 is less or equal to R. The distance between X2 and X3 is less or equal to R, until you get to the end. And so the distance between Xn minus X prime is less or equal to R. So they're kind of like being connected by a sequence of points all within R, like less than separated by by at most R. So it's kind of like that's why it's called like a linkage, because it's kind of like a chain that you build, so like pictorially, you'll see that in a moment. So pictorially, X and X prime are connected kind of by a chain. Where the distance. any two consecutive points is less or equal to R. So yeah, just to wrap it up, and I'll continue this next time, but at least to show you how it looks like in this case, let me copy paste this picture, and I'll finish. This will be the last thing I tell you today, and then next time I'll tell you a bit more about this stuff. It does have like useful applications. But here, like in the case of R equals 1, right? If R equals 1, what it's saying is like the time that 2 points are related, if you can connect them by a sequence of points, and between any of those 2 points in the sequence, like, in the consecutive sequence, like, like their distance is less or equal to 1. So like, for example, like -4, -3, -2 are related because, again, you can in order to go, it's kind of like steps, right? Like you can do like one size steps and rows between any of these 2 points. And then 1, 2, 3 are related, right? For the same reason, like because they can be connected by like paths, like by breaking it up into paths of like 1 and most, and same with 5, 6, and 7, right? But like you see, kind of like these two are not related because to go from -2 to 1, I kind of have to make a jump of size 3, and there's no intermediate points that I kind of can take advantage of to kind of help me get there. So the clusters, because R was 1, right? Like the clusters, you guys have to partition into 3 clusters, and just to do like the other one, like with R equals 2, I mean, you could give it other values to R, which we'll do next time, and we'll talk about something called the dendrogram, which is useful in statistics. But just to finish this up because I'm almost out of time. Right, but if you allow now to jump, now the jumps can be up to size 2. So if the jumps can be up to size 2, then all of these are now in the same cluster. You see, so now there's only, all of these belong to the same cluster, but these are still by themselves, right? These are still by themselves because like the jump here still needs to be 3. And if R had been 3, then all of them get merged, right? So there's only one cluster. So you kind of like see that, kind of like the interesting thing is to consider different possible values of R and see how the clustering like structure is like changes as you change the value for R. So there's like a diagrammatic way to do that, which I'll tell you about next time. But yeah, I think this is like a good place to end. So we'll continue talking about this and more realistic examples. This is just to kind of like introduce the idea. So yeah, next time I'll tell you more about how the clustering works. Ugh. Yeah. That's a very